All right, well, I am still at jury duty, so here is your lesson on section 2.4. Um, I hopefully mentioned this in class on Friday, but if I didn't, if you have any questions from the weekend's assignment, please, hopefully you guys will spend a little time talking to each other about it. Maybe we can get you can get some things worked out. But if there's anything you still don't understand, please send me an email or a message through Google Messenger about which ones, and I will try my best, not promise anything because Monday is packed because I have open house, but I will try to make a video that addresses the ones that you had difficulty on, um, and then you can watch that. All right, so today we're doing section 2.4. Rates of change in tangent lines. So we've done average rate of change. The average rate of change of a function over an interval is the amount of change divided by the length of the interval. Graphically, this is represented by the slope of the secant line. Secant, remember, is a line that goes through a circle in more than one point. Same thing here. To the function drawn through the endpoints of the interval. So if I'm finding the average rate of change over the interval from A to B, it's f of b minus f of a over b minus a. That's the slope of this secant line. We talked about this before, that this equation is a slope line. So, for example, after introducing an organic pesticide to a fruit fly colony, the number of flies dropped from 340 on day 23 to 150 on day 45. Find the average rate of change. Well, as an ordered pair, the input would be 23. There were 340 because the number depends on the day. And on day 45, there was only 150. So we're just going to find the slope between those two lines to find the average rate of change. So the average rate of change is going to be equal to 340 minus 150 over 23 minus 45. Let's see, that's going to be 190. I believe that's correct. And this is going to be a negative 22. And now it makes me wonder, where the heck is my calculator? Oh, I know exactly where it is. Hang on just a second. You can leave it like that, by the way. There's nothing wrong with it. It doesn't feel as satisfying, perhaps, as it should. As a decimal, this would be negative 8.63 repeating. Fruit flies per day. We always want to give the context of the problem whenever possible. We're not as crazy about it as the folks in AP Statistics are, but it'd be nice to give some context to this. Moving on. So the tangent to a curve, so a secant in a circle was the line that intersected the circle in two places, like this. The tangent line, on the other hand, was a line that only intersected the circle in one point, like so. So the question becomes, well, how do we do that to something that is not a circle? For a circle, it's pretty easy. And you could estimate it on another curve, but what are we going to do? So this is a genius sort of thing. There's a whole lot of uses for the line tangent to a curve at a point, including the direction of motion, optics, satellite receivers, all kinds of stuff like that. So we have what is called Fermat's method for defining tangents. Fermat was a mathematician. I want to say French, but I'm not certain of that. So I'll have to look that up. So if we want to do this, what we do is we find the slope of the secant line through point P and a nearby point Q. Then we'll find the limiting value of the secant slope, if it exists, as Q approaches P along the curve. So just a real quick thing, what exactly are we talking about here? So we have some curve. We're interested in what happens at P. We pick a nearby point Q. We find an expression for the slope of this secant line, and then we find the limiting value as we move Q towards P. Now notice as we move point Q towards point P along this curve, like say we move it over here, that this horizontal distance between P and Q gets closer and closer to 0. You're going to see that in just a moment. So then the slope of the curve is this limiting value, and the tangent to the curve is the line through P with this slope. So let's look at how that would play out. So we want to find the slope of y equals x squared at the point 2, 4, and then write an equation for the tangent line at this point. Okay, so we know the point, we just need to know the slope to write the equation. And that's the first thing, is to find the slope. So I'm going to define a point Q, and its coordinates are going to be 2 plus h. So I'm going to add on just a little bit. So it's a little bit to the right. And then substituting 2 plus h in for x squared, we've got 2 plus h squared. So the coordinates of Q are going to be 2 plus h for the x coordinate, and the y coordinate would be 4 plus 4h plus h squared. So the slope of the secant, or the slope of PQ, is going to be the difference between these. So that's going to be 4 plus 4h plus h squared minus 4 over 2 plus h minus 2, which simplifies to 4h plus h squared over h, which then further simplifies by division or by factoring and then canceling 4 plus h. So the slope of this line is equal to 4 plus whatever the horizontal distance is between them, h. Well, then the slope of the tangent is going to be the limit as that horizontal distance goes to 0, because as P and Q get closer and closer to one another, h, the horizontal distance between them, goes to 0 also. So that'd be, as h goes to 0, 4 plus h is equal to 4. So the equation of the tangent line, so that's the answer to the first part. Then write an equation for the tangent line. Okay. So that's just point slope, y is equal to the y coordinate 4 plus the slope 4 times x minus the x coordinate. You are perfectly welcome to leave it like that on the AP exam, on one of my quizzes, on one of my tests. On homework, your book will pretty much always change this into slope-intercept form, so I am too. But on a test or on a quiz, you're wasting time if you're changing this. This is a perfectly good answer. But just so we can check it with the book, let's see, that'd be -8 plus 4 is -4. What does this look like? Well, let's draw a quick graph. Clear that junk out. Y equals, clear this. It was just x squared. Pretty simple parabola. And y equals 4x minus 4. And let's do a zoom standard. So here's my parabola. And there's the line. And it's a little bit hard to see because I'm a little too far out here. So I'm going to set my left and bottom to be 0 so I can see this a little bit better. So my x minimum is set to be 0, and my y minimum also 0. And now let's take a look. So there is my parabola, and there is the line. And notice how it just kind of skates right along that line. It just barely touches it. Where does it touch it? Well, if we trace this to x is equal to 2, for x squared that's equal to 4. For my line, that's also equal to 4. That's the only point at which they intersect. Now, if we were to zoom in on this point some more, you know how right here you can barely tell them apart? If we were to zoom in enough, this line tangent to the curve would be indistinguishable from the curve if we were to zoom in at the point of tangency enough. That's actually kind of a powerful thing that we're going to make use of later in this class. Spoiler alert. A term that you probably don't know is this one, a normal line. A normal line to a curve is a line that is perpendicular to the tangent at that point. So if we go back to a circle, if we have a circle and we have a line that is tangent to that circle, a line that is normal to that is perpendicular at the point of tangency. Like so. So this is the tangent, and this is the normal. And again, it has uses in lots of different engineering and physics applications. So, here is a way that we can take Fermat's method and make it into an equation. The slope of a curve, y equals f of x, at the point a, f of a, is the number m, which is equal to the limit as h goes to 0 of f of a plus h minus f of a over a plus h minus a, which notice is always going to simplify the denominator to just h. So it'll be the limit as h goes to 0 of f of a plus h minus f of a all over h, provided this limit exists. Sometimes it won't. We'll talk about that another day. So let's take a look at this one. Let f of x be equal to 1 over x. So not something as nice as a parabola as we did on the last one. Find the slope of the curve at x equals a. Where is the slope equal to negative 1/4? What happens to the slope as x goes to infinity? And what happens to the slope as x goes to 0 and to infinity? All right, so let's move this up a little bit. So the slope of the curve at x equals a, so we're going to take f of a plus h minus f of a all over h. So that's going to be 1 over a plus h minus 1 over a all over h. And we want to simplify this. Now, can't simplify it the way we did on the previous problem. What we can do, though, this is called a complex fraction. I've got a fraction within a larger fraction. The easiest way to simplify that is normally to get rid of these denominators by multiplying everything in the numerator and everything in the denominator by both denominators, a plus h and a. When we do that and distribute, the a plus h and the a multiplied by 1 over a plus h leaves you with just a, because the a plus h's divide out to 1. Then when we multiply those by 1 over a, the a's divide out to 1, and we're left with a plus h over h times a plus h times a. So this is going to be equal to a negative h over h times a plus h times a, which is negative 1 over a plus h times a. Then if we take the limit of that as not x, I was just thinking, tell the people not to write x because we're so used to doing that. The limit as h goes to 0 of negative 1 over a plus h times a. Well, as h goes to 0, that's just going to be a times a in the denominator. This is equal to negative 1 over a squared. So for any x value, a, could be 3, could be negative 12, whatever it is, the slope of the curve is negative 1 over a squared. This is a formula for the slope of the curve. When is the slope equal to negative? So, hang on, this is equal to the slope of the curve at x equals a. So where is that going to be equal to negative 1/4? All right, so I need negative 1/4 is equal to negative 1 over a squared, which means 4 has to be equal to a squared, which then implies that a is either positive or negative 2. So there's actually 2 places. What happens to the slope as x goes to 0? Well, as x goes to 0, I'm going to have the slope is going to go to negative 1 over 0 squared. Notice the denominator is always positive, numerator is always negative. So this is going to be a negative infinity. Because the denominator is quite small, when you divide a number by something that's quite small, you get a very large outcome. As x goes to infinity, the slope is going to be equal to, well, my expression is negative 1 over a squared. So I shouldn't say equals because you can't put infinity in here, but if I have negative 1 over infinity squared, so I have a negative 1 over something enormously large, this is going to go to 0. Come in. So if we then look at the graph of 1 over x, let's see if this matches what we have. So clear this out, clear that out. We want 1 over x. Let's go back to a zoom standard. All right, so our tangent line, as we get close to 0, yeah, it's going to be infinite, right? And whether the slope is positive infinity or negative infinity doesn't really matter a whole lot on this because it is a vertical tangent line. As x gets really big, we can see that any tangent line would have to be nearly horizontal. So this f of a plus h minus f of a over h is called the difference quotient. You'll occasionally see that used in some textbooks. It's the change in y over the change in x for those 2 points. So here's a question for you. Does the curve f of x equals negative 2x for x less than 1 and x squared minus 3 for x greater than or equal to 1 have a tangent at x equals 1? And it says to explore this graphically. Well, so let's take a look. Let's try it by hand first, and then we'll talk about how to do this on a calculator. So until we get to x is equal to 1, we want the equation to be y equals negative 2x. So that's going to go through the origin and have a slope of negative 2. So if that's negative 1 and that's negative 2, it's going to go to here. That's going to be an open circle because this is not equal to. So it looks something like that. And here we have x squared minus 3. So at 1, that's going to go through the point here. And if we were to graph the whole parabola, it would be here, but we don't have this part. I'm just going to kind of draw that in a dotted part. And then it's going to be going, let's see, by the time we get to 2, when x is 2, this is going to be 1. So that gives me a point to aim at. So the question is, do we have a tangent at this point? And if we were to kind of zoom in on this, no matter how much we zoom in, it's going to look like that. How do you have a tangent at that point? You could draw lots of lines that went through that point. There's not a tangent. There could be lots of lines that go through that. So does it have a tangent at x equals 1? The answer to that is no. How can we draw that on a graph? Well, let me show you. You can use your calculator for that. We go back to y equals and clear this out. So to explore this graphically, you may be wondering, well, how can I do this? Well, it's pretty slick. What we can do here is go, okay, got to turn that off. So I'm going to have negative 2, and there's actually a test feature built into your calculator. If you go to second math, there's all these different logical tests. We want x to be less than 1. So it would have been nice if I had typed x first. I'm going to multiply this times x second math. X is less than, that's number 5, 1. And what's going to happen is that's going to return a 0 if this is not true, and so it'll cancel this out, and a 1 if this is true, and it'll use this. Then plus the second part, which was x squared minus 3, so x squared minus 3. And again, I want to multiply it by the restriction, x is greater than or equal to, that's number 4, 1. And let's make sure we're still in Zoom Standard. And here's what that looks like. That's not what that looks like. What did I do wrong? Hang on a second. Negative 2x for x less than 1. Oh, I have an extra x in here. I don't know how that happened. Plus x squared minus 3 for x greater than 1. Yeah, this is why it helps if you know kind of what the graph looks like before you put it in your calculator. Okay, so if we kind of zoom in on this point, so zoom in on the point, what was that, 1, negative 2? So I'll get close to 1 and close to negative 2. This is what that looks like at this point. And I could spend all day long zooming in, and that's never going to look like a nice, smooth curve there. So there's not a tangent there. A tangent has to be just 1. And from a limit perspective, what's happening is the tangent lines over here all have negative slope. The tangent lines over here would all have positive slope. They disagree with each other, so the limit does not exist. All right, that is it for today's lesson.